So I'm going to talk about Psana, which is kind of the LCLS specific data analysis. There's advantages and disadvantages to this. If you move between experiments at different places a lot, maybe something more portable, like we're thinking at the higher, more portable level of CCTBX or CAS or something like that might be better. But the advantage here is that we support everything at LCLS. So not just crystallography, but all the other experiments that happen. So a little bit of background about myself. I'm kind of a jack of all trades, I would say. I was trained as a high energy physicist. And as a matter of fact, most of the people at LCLS who help you guys with the experiments, we're all high energy. Many of us are high energy physicists. So we're in some ways we're kind of like a conquered race, I think. But in another way, it's a good thing because I love high energy physics. But about a decade ago, I started to feel pretty strongly that scientists need to work on more practical stuff, because I think the world has some significant problems. And so it's really exciting for me to hear about the crystallography stuff that you guys are doing. Yeah, I find it very exciting to work on LCLS. Okay. Yeah, I used to run the data acquisition group, so we designed and built the data acquisition systems for all the LCLS hutches. And then I went away from LCLS for a few years, and I worked on some catalysis software. And then I just recently came back about 8 months ago, and it was decided that this analysis effort could use more help. So I've been working on that. Okay, so the goal, what's the goal of my talk today? I think I have an hour, right?
Yes.
Yeah. Is you should be able to run and understand, I'll call them simple Psana Python examples. Okay, simple is going to be, the most complex example is going to be 46 lines of code. 46 lines. The simplest ones, you're going to see 9 lines, just handfuls of lines. But this 46-line example, okay, it's going to access LCLS data, obviously. You can run this 46 lines in real time online, or you can run it offline. You can use this 46 lines will randomly access events. So you want to jump immediately to event number 30,000 in your file. This 46 lines shows you how to do that. It's got real-time plotting built into it. So if you run it online, and this is, all of these things are fairly recent additions to the Psana analysis. It's changed quite a bit. For reasons I'll discuss in a little bit. It's got real-time plots. So what people have been doing is that Slack has some standard monitoring for real-time feedback, but it does a finite number of things. And there are many experiments where that's not sufficient. People want to do FFTs, but see the result in real time. So here you could call a Python FFT program, run it online, generate a real-time plot, and have instant feedback that you can give to the accelerator. And as well, it runs in parallel, this 46-line script, and I'm going to run it in parallel for you. In principle, on thousands of cores, so on multiple nodes. And this is actually one of the main points of my talk today, because I think, and this is more to the developers, I know the workshop's not geared toward the developers, but I think we have to think more about parallelism, because the data sets are large, and there's been some parallelism in what you guys have talked about, mostly multi-threading stuff. But there's this parallelism called MPI, where you can distribute across nodes. And that is more powerful. And I think that you guys should think about that stuff for the future. So you're going to see this. And this is allowed, and you can run in parallel online as well. So you can take this 46-line script, and you can run it on parallel on multiple nodes, and analyze all 120 hertz online. And there have been now, since we introduced this feature, there have been, I would say, probably 8. We have this feature maybe for about 4 or 5 months, 5 months, and maybe 8 experiments have already used this to analyze all 120 hertz with their own simple code. Because Python is a very simple language. It's not like C or C++. It's, yeah. So, and you can run this, on your laptop, including the parallelism. You can run it on your Mac, you can run it on Windows using this virtual box idea. And so the software that I'm going to show you is going to run on this laptop. And that's something that it's been, it's again a new feature. You just wrap the whole operating system into this one file. It's about 1 gigabyte. It takes about an hour to install or something like that if you have a good network connection. But you might want to consider that for some of your software, CCTVX or Cheetah or CAS or CRISPL. You could put it on a virtual box, and that way people, when they're sitting on the airplane or they could be vacationing in the woods, but instead of vacationing now, you get the opportunity to work. So that's the beauty of technology. You can now work all the time. It's just awesome. Okay. All right, so that's the goal. We're going to start out with a shorter example, but this 46-line example is going to catch up. Is going to be a little more comprehensive. All right, so I'll just go through this stuff pretty quickly. It's this photon systems analysis. It's maybe comparable to what you've heard about CAS or Cheetah as being kind of a low-level thing. It's based, you can write your code in C++ if you're feeling masochistic, or Python if you want to do things a little bit slightly more slowly, although you can do pretty well with Python. And you can buy your way out with parallelism, because LCLS has thousands of cores now. We got 2,000 cores donated to us about a year ago, and a year and a half ago. And they sit idle a lot of the time, except for mostly Nick. Nick likes to use them. Let's see. So one of the weird things about Psana, I should probably speed up here a little bit, but when LCLS turned on, I was doing the data acquisition systems at that point, and there was no offline LCLS supported offline analysis software the day that LCLS turned on. When people were coming up to me because I knew about the data from data acquisition, they said, how do I import my terabytes of data into Excel? And I don't understand, to this day I don't understand the reasons for this. I think it's because the community wasn't prepared for how challenging the analysis problem was going to be. So there was we made something up that was kind of quick and dirty in C++ called MyAna, and then there was PyAna, and now there's Psana. So this thing got a late start. And so this is kind of a work in progress, and that's why a lot of the features you're going to see today, which I think are powerful features, in my very biased opinion, that's why they're just showing them now. All right, so let's keep going. So we have the same idea as CAS, that you can have these reusable modules that can be chained together in a serial fashion. But we're actually, defining the modules in the chain ends up being like a complicated language, in my opinion. And so we are emphasizing more now with Psana, putting logic, like filters on your events, just in Python. A filter is an if statement, you know? You say, if the shot energy was less than this, I want to throw away this event. That's an if statement. And it's much easier to put that in a line like Python than it is to have a configuration file of chained modules. So we have, okay. Let's see, we have support for detector calibrations for CSPAD. We're about to expand this quite a bit. I'm going to go into this. Okay, and you're going to find I'm going to repeat myself probably too many times during my talk. The same software runs online and offline, real-time plots, parallelize over events. You can go do 120 hertz online. Many experiments have done that. A downside of it is LCLS specific. You can't go over to Diamond or something like that, and you can run it. It's not specific for crystallography. That's why CCTVX kind of layers itself on top of us. They layer on top of PyAna, but it should be a relatively small change. We're going to do it in a couple weeks, I think. We're scheduled to sit with Nick and we'll change the layering so it's on top of Psana. So we're recommending this Python stuff to users because it's easy, it's free compared to MATLAB, no licensing stuff. Python, I think, is comparable in complexity to MATLAB, I would say. I'm not a MATLAB expert, but I've used it a little bit. It's a powerful, state-of-the-art language. And it's got lots of reusable algorithms out there. So you can, if you want to go do something, like numerical, there's a whole big thing, SciPy. If you want to do wavelets for filtering, you can do that. We're using parallelization. It's a little bit slower because it's an interpreted language, but a lot of the numerical stuff ends up happening in C if you call the libraries, which is what most people do. And you can use, if you are slower, you can use parallelism to overcome the CPU limitations. And not just CPU limitations, but many LCLS analyses are I/O bound. You got so much data that you don't really need the cores. You just need to get the bytes moving. And but the parallelization, if you can parallelize over multiple nodes, which I'll show you with a 46-line example, that helps with the I/O as well, because now you got, if you're running on 100 nodes, you got 100 nodes worth of bandwidth to the file server. And the question is, how much can the file server give you? But the file servers are also parallel these days. So you got, so parallelization helps with the I/O as well. And then I'll show you some cool self-documenting features, because if you're like me, you hate reading documentation. It really just no fun. You can't find it, or there's too much of it. And so with this stuff, I'll show you, if you only know your experiment number and a run number, you can start playing with the data without, you have to know a little bit of a few lines of Psana, but you don't have to go read anything really. Well, you'll see what I mean, and then you can decide if you agree with that statement. Okay, so it's used by CCTBX, many LCLS experiments in all hutches, because we support every detector and every experiment. And some people use MATLAB analysis on HDF5 files produced by LCLS. And Psana also produces those HDF5 files, these standard format, some people call them translated HDF5 files. But these aren't as real time, which is a problem, because you really need the real-time feedback in many experiments. So this workshop's about BioXFEL software, but I think you may also want to play with LCLS data using Psana. How is the beam energy changing? What's the range of the voltages on this diode? And with writing a few little scripts, you can do that and plot those things out. It's not, I know people find XTC, which is a format that I brought over from my last high-energy physics experiment, because we were short on time. We only had 2 years to develop all of LCLS data acquisition system. And by using XTC, we were able to do that in a relatively short time. It's not, unfortunately, it's not portable, but it's not that scary a format. And then if you write these little scripts, you won't be quite so freaked out about it. At least that's my dream. All right, so now we're going to do, you guys, if all goes well, you guys are going to run your first 17-line Psana Python script, which is going to access and plot the data. All right, so what we're going to do, we're going to go to Confluence, and I'm going to kind of walk through you. We're going to go to confluence.slack.stanford.edu.
So, log into the machine. Trust.
Key point here, this is being slow to load for me because everybody's doing it. Key point here is just to get logged into Psana, which many of you have already done, but we're just going to kind of step through it, especially since this is the first one of the day. Then you go find over on the right-hand side here, LCLS data analysis. And this is where all the documentation for LCLS, Psana style LCLS data analysis is. So then you go to the fifth one down here, and you click on Psana Python interface. Am I going too fast for people? I'm still able to slow down. Okay, so this is our first thing on Psana, and this is a quick example. Okay, so so this you hopefully have already done. You've logged into Psana, to PS Login, which is kind of that's the gateway to the LCLS world. So now, from there, you can now see all of LCLS. And then you're going to go to the Psana nodes, which is where you do analysis. And you have to go here because in order to see the data, for example. Because not all nodes have a fast connection to the petabytes of data that we have. All right. So now we have to get the environment. And we're almost done. We just have to do these 5 more lines, and then you're done. So the goal is in sight. Okay. So let's see. So one of the difficulties is there's 2 types of shells. And there's something called a C shell and a bash shell. So if you can cut and paste, I would try this line first, because I think that's the default shell. That's Slack. If you know which shell you use bash, type this.
Default is bash.
Is that right? Oh, okay.
Okay, so I didn't do anything and I have bash.
Okay.
So.
Then maybe try this one first. And if it doesn't work, try this one. And this is just setting up environment, LCLS environment.
Executes the script and imports some files. Okay. Okay, good.
Okay. Also, Jason is a super expert on this stuff. He's at the back of the room. Do you want to raise your hand, Jason? If you do have issues with this, if it's not going as smoothly as you'd like, can you maybe raise your hand, and Jason can hopefully help? We'll do our best. And later on in the day, I'll do my best to come around and help people as well. Okay, so since I didn't see too many more hands raised, I'm going to keep going. So then we do this rather unfortunately named sit setup command, which I don't like. I wouldn't have called it that if I hadn't. This is setting up analysis specific environment. So so this is getting kind of all of Psana set up.
The next command is copying a Python script.
Yes.
But do we really want this in our home folder? Or
that's fine. Yep.
So anywhere.
Yep. Anywhere.
A related question, is it okay if we do this in the my release directory that we've set up for CCTX? Or
yeah,
would there be contention?
I believe, yes, I believe that shouldn't be a problem. Okay, so then, yeah, this is copying the file. And this is the 17-line script. Okay, and now it's time for the rubber to hit the road and run Psana. And if that all works well, then what you should see is this. I'm going to be, just to show you it can be done, I'm going to be running all this stuff on my laptop. And this is, I need no network connection to do what I'm doing here. And you can do this too on your Windows or your Mac or your Linux laptop. You can get this whole, it's like a whole machine. It's called a virtual box, which I told you about before.
Does this require a certain version of ANA? I have ANA 0.13.0.
It should be fine for any reasonably recent version. Okay, and then what you should see when you run this program you should see a little image show up like this. And then if you click X, you should see another image. And then if you click X again, the program will exit. So now I'm going to take a poll. Of the people who tried, how many were successfully able to see those two images? Raise your hands.
It's running right now.
Okay. Other people who tried, how many were unable to
Now I see
see?
an image.
Images.
Okay.
Okay.
I see one
All right.
image.
So all right, we'll have to work. Yeah. All right, that's interesting. So there's some failure mode that I don't understand there. I would be interested to understand why it fails for the people who it doesn't work. But we have I would say, a large success rate. It's not bad. Could be worse. Okay, so those of you who were able to see those two images, you've run your first Psana program. You've gone in, looked at the LCLS raw data, and plotted it. All right. I think that's...
So we are supposed to see two images?
Yes, after you click X on the first image,
okay.
a second image will show up, or should show up.
Yeah, it does. Okay.
So you've just gone, read the XTC files, of which there are many.
Yeah, sorry, it's a thing. So this file wasn't marked executable, so I marked it executable.
Okay, we got it.
Which
All right, good. More success.
could do this,
That's another triumph for science.
just like him. Also does invoke Python.
Okay. If you couldn't get it to work, it's not a disaster. It's something we could probably fix fairly easily, I think. And if you are interested to make it work, then bug me anytime today. Just come up to me and say, I'd like to have been able to run that 17-line example. You should be able to make it work. All right, so now I'm going to just step you through the lines in this. Again, this is to make you so you're not scared to go look at the raw LCLS data. All right, so what we're doing here, this is called Python, this little language. Again, it's similar in complexity to MATLAB. There's no compiling or anything like that. And it reads in a fairly straightforward way. So this says, go get Psana, this first line. The second line, we're just saying, this is where you would put your experiment name. So this experiment that so if you're in an LCLS experiment, you get assigned an experiment name. It's typically something like CXI84914 or something like that. And you would put experiment equals CXI84914. And I want to analyze run 22 because that's got some grand lysozyme images. And so that's this. This is just saying, and you can put a list of runs. You can say 15 to 37, 15-37, comma, 22. And it will go and analyze, pick all those runs and analyze all those runs. And then this one, this is tricky, and this is something we'd like to make simpler. There's been a big push, actually, directly from the DOE, is my understanding, for us to make the analysis more accessible, easier for people to use. And this has been one of our responses to this. But this line I'm not proud of. This line, it's kind of complicated, to be honest. We have a way we can make it simpler. And this is effectively the name of the detector here. And you can get a simpler name called an alias, but we don't have that in this data set. And but I'm going to show you a little bit later on how you can get the list with a similar Python command. You can get a list of all the names of all the detectors in your experiment. So even if you don't know the names, you can get a list of them with 3 lines of Python. 3. For any experiment, you can get a list of all these names. Now, this is importing some plotting stuff. And then you can probably guess what this next line, even if you're not very software savvy, you can probably guess what this next line does. So that's a variable equal to 0. And you can probably guess what this line does. So DS is the data source here. And this says, this is a loop, for a for loop, for every event in the data source events. We're going to increment a counter. And then we're going to event get. And then this SRC, which is the source, is this name. And there's this other piece here which you also get along with the name. Again, this is not as pretty as I would like. This is actually, I think, the hardest part of the script, is these names. But this gets the data. And then these final lines just plot it. And then once you get past your second event, then we're going to exit and print time. And you can do this for all LCLS data, if you can get the names, and I'll show you how to get the names there. So that's not so bad on the scale of things. And you can, well, we'll get to that in a second. All right, could be worse. And we'll keep going, 927. All right. So there's just a few other things about Psana. I'm going to skip over this slide. This shows that you get these events from the XTC file, and then you just can put them through these different modules. And Nick uses these modules to do various stages of the crystallography stuff. So here's here's the new features. This is the main thing I think I wanted to communicate. I mean, I'm telling you guys, the users, but also the developers. I think this is, in my opinion, this is an important idea. This MPI parallelization. A lot of you have done kind of thread parallelization, but this MPI parallelization, in my judgment, I mean, I've worked with GPUs, for example, for a few years, and GPUs are not appropriate. You won't get the biggest bang for buck in LCLS, because the parallelism, you get a lot of flops, but you don't get a lot of I/O. But this allows you, MPI, it's the most commonly used multi-node parallelization for science. At NERSC over here, the biggest software, which is what I worked on for those few years I was away from LCLS, is DFT, density functional theory. And so the most flops at NERSC go towards density functional theories, which is solving the Schrodinger equation with this non-interacting electron gas approximation. And it's all MPI. So MPI is everywhere. You go to Oak Ridge, it's MPI. GPUs are good for some problems, but not for I/O-bound problems like LCLS, but more compute-bound problems. And the thing is, it not just scales CPU, but the power of using the multi-node parallelization, you can scale memory. Suppose you're short on memory, which I know some problems are, probably maybe not the crystallography, but I/O. You can scale I/O so you have many guys reading. And I know Nick already tries to do this. It tries to parallelize, and this you can do it better with MPI. But ideally, you would design this into your system, and not as an afterthought. So it's something. This is what I think you should keep in mind, which, in my opinion, is the way of the future. It has batch system support in all major batch systems. So you can tell them, once you got your script written with MPI, you can tell, well, go run on 1,000 cores. And the batch system will take care of finding those cores for you. So by default, Psana provides parallelization over events. But you can do fancier things with it as well. There's some people are doing this multi-tau analysis or using Psana MPI to do correlations between events and doing a fancier MPI. But this is the kind of the simplest parallelization that's applicable for most. So what happens is that, here's the picture. Each node accesses a different set of events in the file. And what you need is this random access, which is something that I added to Psana. This was the hard part. Parallelization was easy. It was the random access that was hard for a number of reasons. The random access means you can jump to event 30,000 in the file, like that, right away. And what that allows you to do is that if you've got your gazillions of computers here, and you've got your one file here, this computer can take a little chunk of this file, and he can analyze those events. And this computer can take the next chunk, and he can analyze those events, and so on. So you can chop one file effectively into many, many pieces as you want, and it can be dynamic. So there's a little bit of integer arithmetic, which you're going to see, which allows you to do this chop, because you need that. A lot of times you need that fast feedback in LCLS. So you want to get the data, and you can scale this as much as you want up here. So what you'll run into is the bottleneck at the file server side down here. Now the file servers these days, they're also parallel. So they look like one disk, but really there's many, many RAIDs down here. And the files are distributed across those RAIDs. So you have lots of parallelism up here and parallelism down here. And you can scale this up until you hit the bottleneck of the disks. For the online monitoring, which I've talked about running Psna online, there are no disks. We did this difficult thing where we multicast the data that comes out of the detectors. And so you end up getting multiple copies of the data on the network for free without any of it ever touching a disk. And that's what allows the online monitoring to analyze 120 hertz in real time. At the same time, other nodes are recording the data to disk. It's this fancy multicast thing, which is really hard, but it's pretty damn cool. And so this is kind of the main slide. That if there's one thing I want you to take away from today, I think it would probably be two things. This slide and the fact that, and the 17-line script idea. Those are maybe the two ideas I want you to take away. Everything else you can sleep through. All right, online analysis. So the same MPI parallelization works. You launch on multiple nodes that are signed up for the multicast groups. And now we're getting into the 46-line Python script, which we're going to run. And you can use it to sum an image, for example, sum an image, although people doing FFTs and stuff like that, at 120 hertz in real time, running on multiple machines with MPI. And in Psana, you can make, if your monitoring doesn't fit into the default online monitoring, you can write your own. And we've got user-definable plots, which you'll see. And another point is that when you're doing this online monitoring, if you use the Psana calibration and geometry stuff, which is one other thing which I'm going to touch on later, a lot of us, and I don't know how to solve this problem, it's hard, a lot of us are solving the same problems. You can see the frowny face that Tom White put on the slide next to geometry yesterday. You hear about Nick, how they struggle with metrology a lot. And we have our own metrology stuff for Psana. And it's a little bit of a shame we've got a hard problem, and as best I can see it, we're solving it. We're taking that hard problem and saying, since it's so hard, let's solve it multiple times. Now, there's reasons for that. It's not easy to just solve it once, but ideally, in my head, we would work together a little bit more to see if we could not have N people solving this problem. At least get a little bit more code use, and that's one of the things that I'm actively working on. I've talked to Nick about it, and we should try, in my opinion, to get that better. Let's see, another problem which I'll just mention because it goes into the 46-line example. So, the data is big, so if you're in France and you can't move it to France, the visualization from Slack, it sucks. It's depressing. You want to look at your data, but you got to log into Slack and look at it. So we've been trying to push on this. So the two improvements, the one I already told you about, you can run full Psana, everything, all the graphic stuff, all the whole computer effectively gets put on your laptop in a gigabyte. So that's one option, and then when you're on the plane, you can develop software on a little bit of data. You can't move the petabytes of data to your laptop, but just a little bit of data, or reduced data, which I'm going to talk about a little bit. And in that, you can do on your laptop, and it's fast. And there's this other thing which some of you are using, this NX technology. This improves remote X11 performance. It's like a virtual desktop, which some of this no machine stuff that some of you may have installed on your computers, and that people have had better results from remote sites like in France doing the visualization. So those are two approaches you have. Okay, so here's the random access to XTC events. What you can do is you can, even when you're running online, for example, running from in real time, you can say, aha, here's an interesting event, and you can save its ID to a little tiny file. And so you get these events, maybe it's events that have a lot of hits, for example, I think in your crystallography language. You could save, these are the event IDs that are interesting. And then here's the code to jump to just those events. It's 6 lines long. You import Psana, you put in your experiment, and your run. And here's a key extra parameter that says we're going to be doing random access. and then you loop over the runs that you have, and you get these list of times from the run, the event times. And then in this particular example, we're going from event 3 down to event 1, skipping by 1. So we'll go 3, 2, 1, but you could go event 30, 20, 10. And this gets it. You go run.event, and you go fetch this particular event. And it will jump to that event and return it, and then you can go get the data out of it.
So the
yes.
events are indexed from 0?
Well, they're not indexed from 0. Really, what the event is labeled by is a timestamp.
But the times are...
So time, this is a big, complicated 96-bit number. And then what you say here,
yeah, but
this is an array index.
Yeah, and it is indexed from 0.
And yeah, this array that comes back is indexed from 0. But the real thing that we use to jump to events, the real label of an event in LCLS is the timestamp. Okay. Turns out it's a crappy timestamp. It's much worse than the timestamps we had in high-energy physics because it's only 17, the thing we'd like to use is only 17 bits long and it rolls over every 15 minutes. And so we have to use this kind of kludged timestamp. It's because of a problem in the timing system, a poor choice in the timing system for LCLS. But I'm just complaining. All right, so now this is the 46-line Python script, and I'm just going to run this myself because I think.
Where do you see the script on the Confluence somewhere?
Can you see this script on Confluence somewhere? Let me put it right now in my home directory. So, sorry, it's done.
But I fear we are not allowed to access your home directory.
I think you should be. So if you do a command, I could be wrong, but we'll try it out to see for those who won't. If you do something like copy ~CPO on psna, ipsn, it's called MPI underscore psmon.py. If you do a command like this, copy ~CPO MPI under psmon.py.
Permission denied.
That sucks. All right, I'm not going to fumble around here anymore. I'll fix it up at the end of the talk, and we'll look at it together on the screen. Sorry about that. I should have put that someplace publicly accessible. All right. Okay, so we're going to just run it here. So this is starting up the real-time plot. Okay, and this says this is the name of the plot, and this can be on because it's from a Princeton camera, from some XCS experiment, I think. And this plotting can be on a different node than where the analysis is running. It'll go get the data over the network. That's a similar idea that's built into CAS, for example. So this starts up the plotting, and then and now we're going to run the analysis. So here you can see MPI. So you're searching backwards, but you can see the command here is MPI run -N2. That says run this command on 2 cores. You can bump this up to 1,000 if you want. There's some, to run a multi-node, there's another file. You have to tell it which nodes those 1,000 cores are going to be on, which I'm not going to do here. But it's as simple as this, and then MPI will take care of launching all the processes, and more importantly, it gives you the ability to gather back the results as well. That's a hard problem. And you'll see that in the code when we look at it. So this is going to launch it. It's going to run this little 46-line script, which we'll look at in a minute. And it's going to send out the monitoring data, in principle, to another node, but I happen to be running it on the same node. There it goes, and there's your real-time plot. You know, you're looking at the image. Oh, it's getting too bright. You want to grab it, rescale it. This is kind of a thing called PyQt graph. So you can play around with the plot here and see there's a little where I'm dragging the mouse. This is the kind of the real-time plotting package that we're using. It gives you for 2D images. It gives you this nice little histogram of all the pixel values here, so you can know where to put in the limits for your colors and stuff like that. Okay, so we just ran that on 2 cores.
People should have access to the MPI. They can copy it.
Oh,
Yeah.
Okay, from my home directory? Huh.
Oh yeah, it works.
Okay, great. Yeah, so try it if you want. Try that copy command. Thank you, Jason. Okay, so so now let's look at the example. And again, what we're going to see here, even though it's just 46 lines, you're going to see in this example MPI parallelization. You're going to see this idea of the script works kind of online and offline. You see the real-time plotting. You just saw it running on my laptop. All of this is on my Macintosh here, no network stuff. And also this XTC file random access is all built into this. Okay, so looking at the script. Okay. So here's some stuff. This is just setting up MPI. It's 4 lines. And the key idea here is the rank. So if you're running on 1,000 cores, then each core gets a different rank. The first core might get rank 0, the second core gets rank 1, and so on. And that's how you make the code do different things. So this is a key variable. Then here we're just importing Psana. And we're importing the real-time plots right down here. And then this is our usual stuff. This is the experiment we're analyzing. This is the run. This says that we're doing it with the random access mode. This is that ugly line that you saw before, which is the name of the detector, which we're actively working on trying to simplify, because that's not a fun line to type. Publish is we're publishing the real-time plots. So this is initializing the real-time plotting. And then we're going down the file here. Some event counters for bad and good events, because it's one thing you have to keep in mind. LCLS, especially with this multicast, you can drop events because we're multicasting the data. And it turns out that's not a reliable protocol. And so we had to work really hard to make it as reliable as it is. But you can drop events, so you can request an event, or a detector, it may not be there if the network has dropped it. And that's only when you're running online. Offline, everything's reproducible because you're reading from disk. All right, and then we do the same thing. We loop over our runs. We get our list of times in the run. This is a little bit of math. These 2 lines here is a little bit of math to say, if I'm MPI rank 0, I'm going to analyze these times. So this is a line of Python that's picking out a subset of the times. This is effectively slicing up the file into pieces based on which MPI rank I am. So this is the chopping up of the file into pieces, so that the first rank will analyze the first piece, the second rank will analyze the second piece, and we'll all do it in parallel. And then for your times, because this script is, if we're running MPI run on 2 cores, there are effectively 2 copies of this script running. If you're running 1,000 cores, there are 1,000 copies of this running, and they all differ only by the value of rank. So this is how everybody gets their different set of events to analyze. So then you get those events that just for your particular rank, get the Princeton data, and then this is just a little bit of code to sum it up. So sum plus equals Princeton data. That's how you add two images together, and that's what you saw, the image accumulated. So we're almost done. Okay, here's the key line. This is the communicator, this is MPI adding up the results from the quote-unquote 1,000 cores. So this says, take the sum on each core and put it into this variable called sum all. And MPI has all sorts of operations, maximum, sum, subtraction. It's all sorts of crazy stuff. So this is the simple. The default operation here is sum. There's a third argument that you don't see, where you can specify what operation you want to do. And there's asynchronous operations as well. And then here's the last thing. If I'm rank 0, that means if I'm kind of the master of all these parallel processes, then I'm going to send this data to the real-time plotting. And here it looks like I'm doing it every 10th event. So I'm counting events here. If the remainder when divided by 10 is 0, and if I'm the master core, then I'm going to send the data to the real-time plotting. All right. So now, let's go back. Not bad for 46 lines, I propose. All right, this is getting close to 12:37. Okay. So what do? You show up at LCLS, you only know your experiment name and a run number, maybe. And documentation sucks. So what do? So I'm going to show you this last example here. There's this a special form of Python called IPython. And it's got a little more stuff to it. So suppose you only know, this is all you know. You know your experiment name and your run number. So these are the 3 lines that get you the list of all the detectors, everything. The data that comes from the accelerator, it's all from these 3 lines. So you're going to just put those into IPython at the prompt here. Looks like we get the wrong things. Sorry about that.
It's just
so this is the list of all the detector names that are in here. You can see like the Princeton that we looked at is here. There's another Princeton down here. There's diodes all on here. Here's some data from the accelerator, the E-beam data with the photon energy stuff. So you can get all these names, which are too complex, but it's better, and we're trying to make that simpler. But you can get all these names. So now you've got the names, and say you've decided that you're interested in this Princeton data, but you don't know what to do with it. But now you've got the name. I'm not expecting people to do this stuff with me, just more to watch. So we got up to here, we got all the names, so we can put the name in now. And here's the key idea. So now we can get the data from the Princeton, but we don't know what to do with it. And what I want to say is, what you do is this. Again, you paste those few lines in. So now you've got your Princeton data, but you don't know what to do with it. So what you do is this. You Princeton dot, and then you hit tab. And when I hit tab, then you can see all the methods for this object. And you can do this with a CSPad. CSPad's a complicated device. There's a hierarchy of stuff. You can go get the CSPad object, and you start hitting tab, and you start to see the layers of the onion. You know, you see something that gets you a quad. Then you go get the quad object, and then you hit tab again, and you can go see inside the quad are these ASICs. And you can go and you can get all the CSPad data without reading documentation, by just taking some judicious guesses. So you can see, you would guess here that the Princeton.data might give you your data thing. So you type that, and it turns out, it gives you this kind of weird error. It says, this is a bound method. This means it's a function, and what that's telling you is that you really needed to put brackets around it to call a function. And then here's your Princeton data. And you can do that with the eBeam BLD, so you can figure out here how the LCLS data and what routines to put into your little script, what calls, to go get the raw data with at least minimal reading of documentation, or just a few lines. Okay. All right. So now we'll just try and quickly finish up, I think. Sorry. And a lot of people use this tab completion idea inside IPython. It only works inside IPython, which is kind of an extended Python. Okay, so I'm going to finish up here. I'm going to relatively quickly go through some of the remaining, and all of these are relatively new features in Psana, I would say within the last 10 months or something like that. So we have better calibration support, just like the rest of you guys are doing geometry, bad pixels, common modes, dark subtractions for CSPad and for other detectors as well. You guys focus mostly on CSPads. And we have these tools for generating that in a run-dependent way. So that dark images change as a function of run number, geometry changes as a function of run number, and we have a kind of little file-based database that we use to store that, and there's a GUI, and every hutch uses this. And these same constants get used by the LCLS real-time monitoring. So in the Psana world, you get the same constants right from online through Psana. And it'd be nice if we could, over the long term, get some reuse of these things. You guys have done your own, which is fine because Psana was late to the game for reasons I don't completely understand. But it's kind of a shame we're doing the same thing. Especially for the geometry, since the geometry is a hard problem. That's all I'll say about that. Detector geometry, ideally we solve it once, not multiple times. I'll just briefly say, we do this standard HDF5 conversion from this XTC format. We have this ability now where you can choose which data you want to convert into HDF5. So you can take your big LCLS data, translate it into with the Psana HDF5 translator, and choose what you want, including adding your own data there. Maybe you make it small enough so you can put that data on your laptop and you can analyze it with Psana Python on your laptop. Algorithms. There's a lot available in the Python modules. With SciPy, we don't have crystallography stuff. I don't think we ever will. That's too specialized for Psana. We're trying to be more of a general tool. But it's nice that CCTVX sort of built their stuff on top of Psana, I think. You can use lots of stuff in SciPy, but we do have a central repository of reusable algorithms, like calibrations, radial integrations, cluster finding. Many are written in C++. We're now starting to do Python, and this is a high priority for us to add more algorithms. This is another key point that I want to mention that you guys should be aware of. More and more important devices are not in the DAC data. Mohammed had this problem in his last CXI experiment. He phoned me up and said, I want to look at one of the spectrometers in, I think it was an HXR spectrometer or something like that, Phi spectrometer, and it's not in the DAC. This is because these devices, the DAC has to be on this subnet, which is specific to the hutch. I won't bore you too long with the technical details. But there's these devices which need to be used by all the hutches, so they can't be in the subnet, so they can't be part of the DAC. So, and this is going to happen, I think, more and more. And with Psana, you can see this outside hutch data, which I know Mohammed wanted for his experiment. It wasn't quite ready when you tried to do it, but it is now ready. So keep in mind, this is a hard problem, joining this outside hutch data together with the DAC data. This is not trivial, because it turns out the timestamps are different because of the messed up timing system, which I talked about before. Okay, I think that's it. So I kind of went over these new Psana features. The growth areas are the algorithms. I hope with the detector geometry we could get more reuse, because it's such a hard problem. So I'm going to try and work with Aaron and Nick, and I haven't talked to Tom very much, or Anton. I don't know if we can do, but maybe we should try. Maybe we can talk about it over lunch or something like that. You can tell me that this is impossible. Yeah, and then we're working on easier data access, like simpler names, like more uniform access methods. And hopefully you get the idea that you can do it with a 17-line Python script. It's not that bad to access the LCLS raw data. Most of you have done it with that 17-line script. Okay, that's it.